Hi friends, we'll start with cyclotron. Cyclotron is a machine that is used to accelerate charged particles or ions to higher energies. Here the E and B are the crossed fields. I mean, the electric field and magnetic field are perpendicular to each other. So they're called as crossed fields. Well, the key of cyclotron or the main principle on which this machine works is that the frequency of revolution of charged particles in a magnetic field is independent of the energy of the particle or the velocity, I should say. The two semicircles which you see here are they're called as D's. D, I mean the English alphabet D, D for dog. Just because they look like D, they're called as D. And this is D1, D2. Okay, they're actually metal boxes, and inside the metal boxes, when the particle moves inside the metal box, it is not affected by electric field. They give that shielding, okay? And magnetic field anyways acts throughout the motion. Let's go into the topic. A charged particle starts from the center, say. Observe that there's a constant magnetic field going into the paper, this thing. So if it is a positive charged particle, it moves in this way, which you see. Let me give the arrows to give the direction. Let me explain you. What happens here is when it is the D, inside the D, it is not affected by the electric field. Now you may ask, where is the electric field anyways? These two Ds are connected to a high frequency oscillator. So what this does is it just changes the polarity of these two Ds. At one moment, this D is at higher polarity and the other D is at lower polarity. Say when the particle is here, this ensures that D2 is at higher potential than D1. So what happens is this particle gets attracted to D1 and hence it goes like this. And in this process, when it travels this distance, this short distance, it gets accelerated. So the velocity of that particle increases and hence the radius of its subsequent motion, circular motion, also increases, because you know that the radius is Vm by Qb. I discussed about this in the last video, remember? So as the velocity increases, the radius also increases. Hence, the subsequent motion from here to here, it is a part of circle. It's not necessary that it should be a semicircle anyways. It will be a semicircle when the particle enters perpendicular to this T. matlab, if it enters like this, if this is 90, then it will be a semicircle. However, that's not so important. As the particle travels through this distance, it is not affected by any electric field. And what happens here is, by the time it reaches this point, this high frequency oscillator, it changes the polarity. Now it ensures that D1 is at higher polarity than D2. So the particle again gets accelerated when it travels while it travels from this point to this point through this distance. Again, the velocity of the particle increases and the energy increases. So the radius of its subsequent circular motion also increases. That's why you see that the whole motion or the entire path is something like this. It is increasing in radius, approximately spiral. And what happens finally is when the final radius of the path of the particle reaches r, which is equal to the radius of the d, then it is deflected by some magnetic field placed here. So it is again collected by a target and used for further bombarding or something like that. Hope everything is clear till now. Now let's do some maths. The time period of that particle or one cycle of that particle, it is given by 2 pi by omega, where omega is the angular velocity, and as you know, this will be the final expression qb here. Okay, so if this is the time period, what will be the frequency? It will be qb by 2 pi m, 1 by time period, right? This is known as cyclotron frequency. and I have to apply a potential difference, right? Or in other words, this high frequency oscillator, if the frequency of that oscillator be VA, say, if this is the frequency of that applied voltage, so that the polarity of the DC is reversed from time to time. The resonance condition is that VA should be equal to VC. This is the resonance condition. If this is ensured, then the polarity is changed twice in every cycle. In resonance condition, the polarity of the D's is reversed in the same time that it takes for the ions to complete one half revolution. Let us solve a problem now. A cyclotron's oscillator frequency is given as 10 megahertz, and I want to find the operating magnetic field for accelerating protons, and the given information is that the radius of D is given as 60 centimeters, that is 0.6 meters, and also I'll find the kinetic energy. Okay, you know that the frequency is QB by 2 pi m, right? Now mass of a proton, I know it as 1.27 into 10 power minus 27 kg, and I know the charge also, it is 1.6 into 10 power minus 19 coulomb. So frequency is given, right, 10 power 7 hertz. So you can find it, just put the numbers, you'll get it as 0.66 Tesla. Okay, now velocity, how to find the velocity? For that also you have this formula. All these formulas are derived in the last video, I guess. So you know the radius, right? The final radius. This is the final velocity if this will be the final radius. And what will be the final radius? It will be the radius of D itself, because it emerges out of the D, right? If there are two cyclotrons which are using or which are operating with the same magnetic field, then I can say that the particles come out with greater energy out of the cyclotron which is having a D of greater radius, because energy is directly proportional to V square velocity, right? And V is given by this thing. R will be the final R, capital R of the D. So you got it. And put the R is 0.6 here, and you know the charge, you know the magnetic field, you calculated it here, and mass is 1.27 into 10 power minus 27 kg. Put all the numbers, you will get the velocity something something. You will get the velocity to be 3.78 into 10 power 7 meters per second. Now, how to calculate the energy? It is nothing but half mv square kinetic energy, and here you are going to get the energy in terms of joules. Okay, and there is something called as electron volt. It is also a unit of energy. 1 electron volt is the energy that proton gains. Proton is having 1 e charge, right? 1.6 into 10 power minus 19. When the protons travels through a potential difference of V 1 volt, then the energy difference will be, potential energy difference will be 1 electron volt, and 1 million electron volt is nothing but 10 power 6 into 1 electron volt. So converting this, which is in joules, into electron volts, you get the final answer as 7 million electron volts. Say you have a conductor here which is carrying some current. Take an element here, DL element, which is carrying the current I. Now I want to calculate the magnetic field due to this element only at this point P, which is at a distance R, and I'll explain about direction later. This magnetic field due to that element only was found to be proportional to the current that the conductor was carrying, and also the length of that element, and it is inversely proportional to the R square. I'm writing it like this to give the direction, or I'll tell you this dB. To remove this proportionality symbol, I'll put a constant that will be mu naught by 4 pi. ideal. This is cross product again. This is vector product, and r is the radius vector. This is, I'm writing it as a vector to get the direction of the final magnetic field. You can as well write it like this also. Let me write it for you. Ideal r cap by r square. This is also fine. Just to get the direction. Okay, how will you get it? Again, by right hand rule. If dl is a vector having this magnitude and direction of current, and r is your radius vector, the vector product is what? You can get the direction through right hand rule. Move your right hand fingers from this dl to radius vector this way. So your magnetic field will be in this direction into the paper. Okay. Hope everything is clear till now. Now, this constant mu naught by 4 pi, its value is 10 power minus 7 and units are Tesla meter per ampere. Okay, what is mu naught? Mu naught is the permeability of free space or vacuum. Let me tell you something interesting here. In that static electricity, I told you that the electric force is given by 1 by 4 pi epsilon naught into q1 q2 by r square, something like that. Don't you feel that this formula is pretty much similar to that? Here also you have some constant multiplied by two quantities and you have r square in denominator. Actually they are related. Let me tell you how. Epsilon naught is the permittivity and mu naught is the permeability. The product of these two will be, I'll write the same expression as 4 pi epsilon naught into mu naught by 4 pi. Okay. Anyway, 4 pi gets cancelled, so it doesn't matter. And there the constant was 1 by 4 pi epsilon naught. So 4 pi epsilon naught will be 1 by 9 into 10 power 9. And mu naught by 4 pi, as you know, is 10 power minus 7. So finally, what did I get? 1 by 9 into 10 power 16. I can write the same thing as 3 into 10 power 8 whole square. What is 3 into 10 power 8? It is approximately the speed of light. So finally, where did we end? Epsilon naught into mu naught is 1 by c square. Now let's solve a problem. The question is, we have a small current carrying element at the origin, and the direction of current is towards the positive x-axis, and the length of this current element is 1 centimeter, 10 power minus 2 meters. Okay, current is 10 ampere, and I want to find the magnetic field at this point, which is on the y-axis, and the distance between this point and this current carrying element is 0.5 meters. Now just use the formula to get the magnitude. You can just write it as mu naught I dl sine theta, where theta is the angle between the dl vector and radius vector, by r square. Okay, mu naught by 4 pi, of course here it is 4 pi. Mu naught by 4 pi will be 10 power minus 7, and current is 10, dl is 10 power minus 2, sine theta is 1 anyways because the angle is 90, and here you have 0.25, which is r square. We'll get it as 4 into 10 power minus 8 Tesla. Okay, and the direction, it is given by again the right hand rule. This is my dl vector direction. Okay, and the radius vector, here it is in this direction, right? So by right hand rule, my magnetic field should be this one, given by this direction at this point. Okay, what about a point, say 0 comma 0 comma plus 0.5, I mean a point on a z-axis? There the magnetic field will be of same magnitude because r is same and similar conditions, but the direction will be in this. And what about a point 0 comma 0 comma minus 0.5, I mean on the negative z-axis? There the direction will be this one. Magnitude will be same in all the cases,